content of today. I have one organizational topic. 1 second, sorry. The next session in next week, May 6, is Industry 4.0, and then 2 weeks later we have session number 12 and 13, how to digitize production processes without programming code, number 3 and number 4. And due to some organizational challenges, we have to change here the sequence so that we will start next week, May 6, with our TULIP workshop number 3. So we will raise it here up. And then May 20, we will have TULIP workshop number 4. And then on May 27, we will start with Industry 4.0. So at the end, we have to skip to this sequence. So please keep in mind the date and time slots are the same, but next week it's not Industry 4.0. We start next week with, or we go on with TULIP and our session, how to digitize production processes without programming code number 3. So back to our core content, additive manufacturing. We will start with a very short summary. So some weeks ago, during the session number 8, so the first session of additive manufacturing, I showed you our ring nozzle. So here, this part, the yellow one, it's a nozzle for coolant for our machine tools. And this is here the cut model of the inner geometry of such a machine tool. In this case, it's an ultrasonic machine. It's an ultrasonic 60 Evo, so a milling machine. And we have here in gray, this is the milling spindle, and here in yellow, the conceptual design of our ring nozzle. And here marked in blue, this is the coolant, so the fluid we use for the milling process. So this is here the tool holder, and here in the center of the coolant flow will be our milling process with the milling head. And we remember this is the design of our ring nozzle. So the overall view at the top and 2 cutouts, A and B. And we designed it to print it directly with a metal-based printing process. So we have here marked with number 1 with a plain base surface. So we print in this building direction. And we placed all, let's say, complexity in the building direction. And if you have here, look on cutout number B, marked with number 3, we have inner channels like this, and please keep in mind it's possible to print such a channel with a rooftop with an angle larger than 45-degree overlap. We are able to print it directly. If this angle is flatter than 45-degree, we have to print it with so-called support structures. I showed it in session number 8. So support structures are very thin lattice structures printed in the same material, and it's necessary to remove them by milling or turning or to break them away manually. But if you have here an inner channel like this one or here on this side, it's impossible to reach this area with a milling tool, for example. So it's not possible to remove all this lattice support structure in an inner channel. So because of this, we normally, and we find not only in this part, but in more or less all additive or designed for additive parts, we will find overlap angles bigger than 45 degrees. So here and here and in this area. Here we designed let's say a cavity. It's number 4. It's to reduce the material accumulation. So if here is a cavity, it's not necessary to melt the metal powder in this area. And this is, or the reason why we do this is to decrease the building time. Number 5 here is here's a pipe with a diameter less than 8 millimeter, and it's possible to print pipes with less than 8 millimeters in diameter directly without support structures. So normally you can print small channels directly without support, and then it's not necessary to change the geometry of such a pipe. We have here rounded edges. It's marked with number 6, and we have in the inner geometry an allowance for machining and an offset. So we print the part a little bit bigger, normally 0.5 millimeter offset, to enable the final machining later on with a machine tool. And if you want to do the final machining with a machine tool, you need clamping surfaces. And clamping surfaces are here, in this case, in the area marked with number 8, so the inner geometry. And I skipped this slide for today, but it's in the content of session number 8. If we print overlap like this pipe structure here or this area, we need support here under this surface. So, and this is a short summary of the ring nozzle I showed you in session number 8. And you will find some of these routes later on in our design guideline. So perhaps you can compare it later on our design guideline with the design of such a part. So, and I think I showed it already in the last session. This is the finished part, and it's printed in aluminum, and it's already machined. You can see it here in these areas where we want to press in the nozzles. Here are machined areas, and we use a milling machine for this. So let's start with new content. First of all, a short summary of cost structures for printed parts. So let's start with a quality overview. So we will have here at the end 3 diagrams, and on the y-axis is always costs per piece. So the piece cost for a printed part. And we have here in blue is marked the cost per piece for a printed part, and in gray it's for conventional manufacturing. For example, for milled parts or turn parts or cast parts. And on the x-axis, in this case, we have the lot size. And you can see here in conventional manufacturing, it's the typical decrease of costs per piece in this case. So if you increase the lot size, so you produce more parts, then you will have an increase of the price per part. So it's the typical relationship. But in additive, the price is directly allocated to the print time. The print time, it's there's a directly relationship to the volume of a part. So for a specific part, you need a specific printing time. And if you print 2 parts, you need the printing time twice. And if you print 10 parts, you need the printing time 10 times. And so the price, if you increase the lot size, there is more or less no decrease of the cost per piece. So, and this is one special effect in additive. The second diagram here is cost per piece, and on the x-axis is the complexity. And again, in blue is additive manufacturing, and in gray is conventional manufacturing. So if you compare this, normally, if you increase the complexity of your part, so the geometrically complexity, you will get an increase of the cost per piece in conventional manufacturing. For additive, it's unimportant. You can print a solid cube, or you can print a very complex lattice structure, for example. And if the volume, the printed volume, is more or less equal, the price for the solid cube will more or less equal to the price of a lattice structure. So for us, the complexity is unimportant. The effect on the price is more or less linear to the volume or the printing time of a part. And the last diagram it's again cost per piece. And on the x-axis is the light wine, the degree of light white design. And normally, if you want to produce light white designed parts, so for example, for aerospace or planes, you will get an increase of the cost per piece with an increased level of light white design, because it's you need more time in the milling process to cut away material, and so light white design is normally more expensive than a standard design. And you can see it here in additive manufacturing. It's another effect. If you create or design parts with a light white approach, you reduce the weight of the part, and directly you reduce the volume of the part. And with this, you reduce the printing time of the part. And so for additive manufacturing, light white design is an approach to reduce the part costs, because you reduce the printing time by reducing the weight of the part. And at the moment, if you compare to traditional technologies, additive manufacturing for metal materials, it's, let's say, expensive, but there's a development of the machines for this field. So what we see in the past and what we will see in the future, I'm very sure, is an increase of the machine prices, or at the end of the cost per piece of printed parts. So the area where additive manufacturing is suitable will become bigger and bigger in the future, because we are able to realize or create more applications for additive with an economical benefit by an increase of the cost per piece. And if you want to get a more detailed view on manufacturing costs for additive manufacturing or printed parts, this is a typical overview of the manufacturing costs. So most of the costs, typically for standard materials like stainless steel or aluminium or tool steel, the machine costs or the printing costs are the major part of the manufacturing costs of a printed parts. So more than 70% of the manufacturing costs are allocated to the machine costs. And we have some setup costs and material. Typically, material is only 10 up to 15% in standard materials. So to change to a cheaper material, that's normally not an approach to reduce the part costs. So much more effective is to redesign a part, to optimize the design of the part, to reduce the volume of the part, and to reduce the printing time, because at the end, the machine costs are linear to the printing time. And the right design or a design for additive manufacturing is much more effective than to change the material. So this is here too easy. We have sometimes heat treatment, and final machining is normally this is around about 7 or 10%, and some other costs. So this is a typical overview of cost for printed parts with standard materials like stainless steel, tool steel, or aluminium. It's a little bit different if you analyze parts with high-priced materials like titanium, or extremely it's also possible to print silver and gold, for example, for jewelry industry. Then the material costs, or the ratio of material costs, is much more higher. So the title of this session today is One More Step Ahead. And I showed you our first ring nozzle already. This is a single flow ring nozzle. So we have one channel inside for coolant, for a fluid. And this was the starting point to implement such a nozzle in our machine tools and to communicate it to our development departments. And after this first ring nozzle, we started to design a ring nozzle version 2. And our approach, or our conceptual design, is to combine two channels. So our goal was to create a dual flow ring nozzle with, again, one channel for coolant and a second additional channel for pressed air. Because very often we use a coolant to cool the milling area in a machine tool, and we use pressed air to clean the chamber. For example, to bring the chips out of the milling area. And this is our conceptual design. So we want to add a second channel. Here it's our coolant flow it's in red. We have here a coolant inlet at the bottom side. And we have here, it's similar to our first ring nozzle. We have here bores for press-in nozzles. They are here in light blue. And we want to integrate a blue channel, a second one for air. So we have here the air inlet. And normally it's enough to add less air nozzles than coolant nozzles. So we have here two coolant nozzles, then one air nozzle, again two coolant nozzles, one air nozzle, and so on. And this was our conceptual design. And this is one of our actual designs for two-channel coolant nozzles. So again, it's for sure it's for printing, so for additive manufacturing, and again we choose aluminium because it's very light, and it's good to print, and you can print it very fast, and it's easy for the final machining. And you can see here the two channels. Sorry, in this case we have here light blue and red. So again, red is the channel for air, and we have here again, like in the conceptual design, two nozzles for coolant, one nozzle for air, two nozzles for coolant, and so on. And the two channels are integrated here together. So it's one part with two channels. And we have here again the challenge that it's possible to print surfaces or rooftops of inner channels or top surfaces with an angle of higher than 45 degrees to print it without support structure. And let's have a look here in the inner geometry. So we have here a cut through this channel, and you can see here the main channel. This is for our coolant flow. It's the larger one. And we have here a second channel for pressed air, it's the smaller one. And so they are integrated in one body. And you can see here in the cutout that we have surfaces with angles to the bottom surface with more than 45 degrees. So it's possible to print such a geometry without support structure in the inner channels, because again, it's impossible to remove such a support structure there. And here, this is the socket for the nozzle. And in this case, it's designed as a separate part in the CAD system. And finally, we merged in our CAD system all bodies together. And to connect such a socket for a nozzle or the nozzle itself with our coolant flow or our pressed airflow, we have here designed breakthroughs to connect both. So we have here the fluid, and through this breakthrough, the fluid is able to reach here the socket or the nozzle area. So later on, if here is fluid inside, this area is full of fluid, and if you do not connect it here, and instead of this breakthrough, you integrate here breakthrough, you can say this nozzle is now for pressed air. And but you have to make sure there's only one breakthrough is for one nozzle. And I will go one slide back. And so you can see here again the two channels integrated. So here red and blue. And this is the red one, and here's the blue one. And then it depends on the breakthrough. We have here a lot of nozzles or sockets for nozzles. And you can decide by designing this breakthrough, is it an air nozzle or is it a coolant nozzle? So in this case, two coolant nozzles for one air nozzle, but it's also possible very easy by changing the design of our part to say, hey, I want one air, one coolant, one air, one coolant, or it's also possible to say one air, 5 coolant, then again one air and 5 coolant, and so on. So the design of such a part is very flexible, and you can adapt it due to the requirements of our customer later on. So at the end, the customer is able to say or to define the type of ring nozzle he need for his special application. And this is one of the main benefits of additive manufacturing. It's so easy to change the functionality of such a part by changing only these breakthroughs. And here you can see in two screenshots of our CAD models, we designed at the moment, or we have two products at the moment, two dual flow ring nozzles, one for the DMU50. It's a milling machine in third generation, and we designed it also for the DMU60 Evo. It's a similar milling machine, and both parts, if you have a look here, they look they look more or less equal. So, but at the end, the position of the inlets for air and coolant, there is a little bit difference between DMU50 and 60. You can see it here. We have here the inlet directly at the blue coolant nozzles. And the right one is also directly at the blue coolant nozzles. And here at the DMU60, it's in the left area, it's at it's equal, but here on the right side, it's more shifted to the light blue nozzle. But at the end, it's only one parameter in a CAD file, and for us, it's unimportant if we print this version or this version. So this is the CAD model, and this is the real part. So you can see here the printed part in aluminium. And it's already machined. You see it here in the sockets. And you can see it's one line. So if we print a part with growing walls, this area this small line, it's a visual effect. It's there, this area. So we have growing walls, and in the area they grow together, we will get such a small line. So it's typical for 3D printing. And this is our own ring nozzle in our own machine. It's for DMU50, and you can see it here. By the way, this is also a printed part. Also for our machine tools, it's for not for milling, it's for grinding operations. And this is here the situation, our DMU50. You can see here the ring nozzle, and this is the ring nozzle at the end in action. So at the moment, we are using only 6 nozzles for coolant, and you can see here with a very high coolant flow to optimize the cooling in the milling area, because here in the milling area where you create a lot of chips, we will have a lot of heat inside. And to avoid or to minimize the heat and to transport the chips away, we use a lot of coolant, like in this picture. So this is a typical final machining of a printed part by using printed parts. And so this is enough to our second version of the ring nozzle. I will give you now some more information about possible applications for additive manufacturing, and then we will switch to our design guidelines, so that I will give you an overview about rules to design for additive manufacturing. But first of all, here the next topic is hybrid manufacturing. I think only 2 slides to give you a short overview. So what is hybrid manufacturing? For us, hybrid manufacturing is if you compare traditional manufacturing with additive manufacturing, and it's not to do the final machining of a printed part. So for us, hybrid manufacturing is, in this example, it's a tool for a milling machine, and you can see here on the left side, it's a HSK A63 tapper. So this is the base of a tool holder. So this here is the geometry where we fix a tool in our machine tool. And it's a standard geometry. And in this case, it's a turned part. So this part here is traditional produced with traditional technologies. And here it's turned and grinded later on. And we have here a flat surface at the top. And we are normally we print on so-called printing plates, but it's even possible to print directly on other parts. So if you have here such a flat surface, we can clamp this tapper in our printing machine and then print directly on the surface. So you have to keep in mind that it's important that you have similar materials. So it's not possible to print aluminium on a stainless steel part or vice versa, because at the end it's a welding process, and so it's necessary to have the right combination of materials. So, but normally in this case here, it's a steel, and we print tool steel on this. And if the material combination is weldable, then it's also possible to print directly on such a tapper or any other geometry. But it's necessary to have a flat surface to print on it. And here we started to print this geometry, and this here is a PCD tool on such a HSK tapper. And later on, the cutting edges are here at the top. And we have here you can see here some pipes, and these pipes or these nozzles here are internally connected to this hole. So this is for the internal coolant. So this is a channel for coolant fluid. And we guide this coolant fluid with printed channels inside this tool to the nozzles at the top of the tool to bring the coolant directly in the cutting area here. And we have here on the next slide an animation of such a part. And you can see here the printed pipes. So, and this part is not massive built. So if you're in a helix to increase the stability of such a tool, and you can see here very good printed pipes inside such a geometry. So normally it's not such a pipe here, it's integrated in the wall thickness like here, but this is a typical application for additives. So we are very good in printing pipes and channels for fluid or pressed air or whatever you want to guide in such a part. And here again, you can see here, this is like our printing plate at the bottom. And we have here a cavity to fix or to clamp our tapper geometry. And then we will bring or recoat here metal powder on this surface and melt it with our laser, and so print directly on such a hybrid or pre-milled blank. And so this is for us hybrid manufacturing. And typical applications are like this tool for machining, but also for molds for injection molding, for example. So molds for injection molding are often very massive, and it will need a lot of time to print such a massive structure. And in such a case, it's possible to use a pre-milled blank, so the let's say the base of a part, and then only to print the area on it with the complex geometry. So the cavity for the later molds where you inject plastics or aluminum to create a new part. And yeah, that's hybrid manufacturing. And now let's switch to some basic principles. So we skipped it in session number 8, and I want to show you it today. So in session number 8, I gave you a short overview about printable materials. So we have here now the slide for SLM materials. So you can see on the right side, typical materials for metal printing. So very often used is this aluminum here alloy. This is RLSE 10 Mg 0.5. This is a typical aluminum for metal printing. This is cobalt chrome. It's for medical implants, very often used, for example, for tooth crowns or for applications in your mouth. We have here Inconel 625, or it's also possible to print Inconel 718, and it's for applications with high temperatures. For example, in aerospace or for planes, for turbines, and the hot end. So there, Inconel very often is used. And Inconel is very easy to print, but it's very hard to machine Inconel. So this is one of the main advantages of printing Inconel. It's so hard to machine Inconel and so easy to print it that it's often it's not so important that additive is an expensive technology, because it's so hard to machine such a material. It's often economic to print Inconel parts and then to do only the finish machining at such a part. Stainless steel, in Europe it's often called 1.4404 or International 316L. It's a high quality stainless steel. and it's, let's say, together with aluminum, one of the standard materials for 3D printing. So this is very, very often used, especially also for medical tools, for example, for operations, or for tool industry, and sorry, not for tool, for food industry. And so this is a very often used material, the stainless steel. Finally, we have here titanium, often used for space applications. And at the end, tool steel, it's 1.2709. It's a margin steel, and you can harden it. And this tool steel is the standard material for applications from die mold industries. So if you have a look here on such a powder and you use a microscope, this is a picture of such a metal powder. In this case, I think it's stainless steel. And you can see here small parts like this one and bigger particles like this one. So the goal is to have a powder with very circular particles so that they are round, and you need a variation of small and large particles. It's important because when you use the recoater to bring the powder into your building chamber, you want to recoat a very thin area of powder, and it's necessary to have a high density of powder. And normally, if we melt it with your laser, this surface will the effect is that in the powder is air between the several particles, and if you melt it, there's no air inside, and so the density of the melted area is higher than density of the powder, and to avoid problems, we optimize the powder so that there's a variation of small and bigger particles. I think you can guess, if you want to fill a cube, let's say a cube of 1 meter, you want to fill it with balls, and you use only basketballs. There's a lot of air between the balls, and if you use basketballs and soccer balls and also tennis balls and ping pong balls and so on, then you can fill up the area between the big balls by using the small balls, and this effect is equal to this powder. So we use small and medium size and big size particles to increase the density of the powder itself. And let's have a view, or theoretical view, on the exposing strategy. So normally, if we print a part, first of all, we exposure the hedge, the inner area of a part. So here, sorry, in black, this is the goal, the outline of our part. So at the moment, we are printing cubes. And after we exposed the hedge, we expose a so-called boundary line, the outer line, and a second one, this is normally called the fin line, to connect the boundary with the hedge inside. And we have different parameters in our machines for hedge and boundary, because normally you want to print this area inside the hedge, the green one, very fast with a high power of your laser. And it's different with the boundary. So normally you want to get a high quality outer surface, and therefore you print the boundary line here in red with lower laser power and lower laser speed to increase the quality of this surface. And this is a screenshot of our machine preparation software. And this is an area. Here you can see the paths of the laser. So in this case, we have here in green, this is the hedge. And we have here in red the boundary lines, and in this case, small fill lines to connect boundary and hedge. And at the end, this is like the G code in a machine tool. So we use all these paths to control the laser. And at the end, we have here, like my laser pointer, the laser is going path by path, so vector by vector, and melts the metal powder in this area. And if you have a look on a printed surface with a microscope, this is a printed part in stainless steel. And normally, if you have a part in your hand, it looks like one part. But if you have a look with your microscope, this is the surface. And you can see here the area of a air nozzle with a diameter of 0.5 millimeter. So this red circuit is with a diameter of 0.5 millimeter. And then the machine or the job preparation software will control the laser like this. So this is one melting process. And then here we have here the hedge line by line. And you can see here very easy that additive manufacturing for metal, at the end, it's a welding process. So this picture looks like all other welding processes for metals. And interesting is where here you can see so small areas, small particles. These are powder particles that are not melted. So they glue together or sinter together. It's not possible to remove them with a vacuum cleaner, but normally we used sandblasting or blasting with glass pots to remove all these particles on the surface. This works very good. And this is a surface picture of such a surface of stainless steel of a printed part. And if you have a look inside, so normally our parameter development departments, they print a lot of cubes, and this is a cut out of such a cube. Normally it's 10 millimeters in each direction, and you can see here the density of such a part. So all black areas are pores in such a geometry. So this is a bad parameter. So we have here density of 97%. And in this case, also 97.9% density. So this is a bad parameter. It's not a good result. So normally we reach densities of 99.7, 99.9% density. And then you can see here are some areas. The black one, these are also pores, but it's different to casted parts. So we have not one big pore in a area with more material. It's more, let's say, very fine pores all over the part. And so it's this is for us a standard process with such a high density. And at the end, the mechanical properties of such a printed parts are equal to the mechanical properties of a standard part. And everyone want here high densities with 99.9%. But at the end, we are able to control our process. So it's also possible to create parts with a very low density. So this is not a mistake or an error. This is a specific adjustment of our densities by parameter variation. And this is a very cool function. So by variation of our parameters, we are able to create parts with a low density, like a sponge. Or, and please keep in mind, it's not necessary to print the whole part with the same parameter. So we can also create a part with a small area with a low density, for example, for filter functions or other functions where we use sponge structures. So this is also possible with additive manufacturing. And at this point, I want to skip now to the design guideline because I do not know how many time we need to spend on this. And if we are fast enough, I will show you later on one more example of a robot head. But first of all, because it's important for our exercise, I will give you now a short overview about our design guideline. 1 second, we have to change the presentation, the slides. So this is our design guideline for parts for selective laser melting. And it consists, I think, of 12 slides with the real basic principles. And let's start here. And I already uploaded to our session folder in Microsoft Teams. And we have here, yeah, in each slide is one topic. So the first slide is here, overhang and supports. And we created here some, let's say, rules how to design parts. And then we marked here geometries that are not suitable with such an X. And if it is suitable for additive, with such a hook. And so if you have areas with overhangs in your part, it's helpful if the angle is higher than 45 degree, because with, for example, 20 degree or 35, so lower than 45, it's necessary to support this surface with support material. And this is the thin lattice structure you have to remove later on. If you print here with 45 degree or better with 50 degree or 60 degree, then it's possible to print it directly without support structure. The second one here is to avoid plane parallel overhangs like this. So if you want to print such a geometry, it's necessary to print here in this area. In this area here, you need support structure because the angle of the surface is 0 degree, so lower than 45. And it's better to adapt this and to replace them by using angles. Again, 45 degrees is, let's say, the first one, and it's better to increase it to 50 or 60 degree, like this here. This is printable directly. Second is organic design. So in mechanical engineering, often you use very simple geometries like this. But for additive, it's unimportant. We print also such a part. So it's often helpful to use organic designs, which are functional focused. So not function follows form, but in additive is more form follows function. And by using such an organic, or let's say a free form design, it is possible to design functional focus without support structure. So again, we have here an angle with 0 degree, and we have here angles or surfaces with angles of 45 degrees and higher. So this is printable without supports. It's often helpful to use chamfers or radius to avoid edges with flashes. So like this. So here's it's a printed cylinder, and normally at the end it's the effect of our boundary parameter in combination with the hedge parameter. We will get here a small flash, and you can avoid this by using chamfers or radiuses. Again, overhangs. It's possible to print overhangs with up to 10 millimeters, sometimes even 50 or 60 millimeters. So it's not so hard, this rule. And it's possible to print plane parallel overhangs with maximum 1.5 millimeters without support. So 2 slides back or 3 slides back, this here is possible if the length of this area is less than 1.5 millimeter. So, and the building direction of your part is very important. So observe the building direction in the critical geometries. So for example, we have here the same geometry on the upper and the lower side, or the top side or the bottom side. And in this direction, the holes or the geometries are printable. In this direction, again here, the angle of the surface is 0 degree, or in this case, it's 30 degrees. So this is not printable without supports. In this case, it's printable. So if you design a part, you have to keep in mind the building direction. And keep in mind the so-called step effect. So if you create surfaces with flat angles, like this one, 30 degree, this step effect will much more higher than if you create here higher angles, like in this example, 70 degree. Then here, the at the end, the stair-step effect can result in geometrical errors or roughness at the end of the surfaces. And it's depending on the layer thickness and angle of the incline. At the end, the layer thickness typically is 50 microns, so it's not changeable. Because if you reduce the layer thickness, you will automatically increase the printing time. And so often the more effective way is to choose a smart design to avoid or to reduce, let's say, to reduce this effect. So if you want to integrate holes and pipes, if they are designed in a horizontal direction, you normally will get here not a circle, but something it's like this here. It's again our step effect. So these are the slices of our part. If you want to optimize the geometry of such a pipe, you print it in that direction, so in the printing direction. So at the end is the rule is to observe the requirements for drill holes and channels and orientate them appropriately. So the best geometry is in building direction. So one more slide, 2 holes and ducts and pipes. In the first slides today, I showed you in our first ring nozzle that it is possible to print pipes with a diameter less than 8 millimeter. So this is this rule. So horizontal drill holes with diameter more than 8 millimeters will have poor surfaces quality and require support structure. So this is here a hole of 8 millimeters. It's the maximum printable without support, but you can see it here very good. We will get a very poor surface at the top of this pipe. So to avoid this, it's possible to print pipes with another geometry. For example, with such a geometry, they are printable very good because at the end we have here angles higher than 45 degree, or in this case, or overlaps less than 1.5 millimeters. And so, it's useful to change the geometry of your pipe depending on the orientation in your part to avoid at the end support structures. One slide to lattice structures. So it's possible to integrate lattice structures in parts to remove massive material with the goal to, on the one hand, to reduce the part's weight. It's nice for the use of the part later on, but at the end, it's an economical goal. So if you reduce the part's weight, remember to the slides of the production costs or the costs per piece. If you reduce the weight of a part, you in the same step you will reduce the printing time, and so you will reduce the price of the part. So it's possible to create, we call this two-dimensional lattice structures, or it's also possible to integrate three-dimensional lattice structures like this geometry to reduce the printing time or the part's weight. So here at the end, lattice structures reduce weight and therefore costs of a part. If you print cavities after printing, they are full of powder. So if you print cavities without holes or ducts, it's impossible to remove the powder from this cavity. So it's very important to avoid powder inclusions so that it's possible to remove the powder. So therefore we use, like in this picture here, small holes or ducts to remove the powder from inside the cavity. Markings and text in parts. It's also possible to print text or, for example, a serious number into a part. I think for the exercise for you, this is not so important. So keep in mind it's possible to print markings and text. And at the end, you have to pay attention to the font size and the depth of the markings. So last slide of this design guideline, we added here for you a short checklist to check a designed part if it is suitable for additive manufacturing. So why do I show you this design guideline and why do I upload this to our session folder? Because we need for all these sessions at the end, we need exercises. And from my point of view, it's too boring to create here a multiple choice test for additive because we have so much possibilities. And because of this, I created here a small exercise. And these slides are also uploaded to our session folder already. And the exercise is called grinding nozzle. And the goal is to create a design suitable for additive manufacturing for an existing part, the grinding nozzle. And it's not necessary to use a CAD system to design it. Please do it with a piece of paper and a pen. So after 2 sessions, each is 90 minutes, you are no experts in design for additive. But I think you got some rules like your overhangs and support structures. So it should be possible to create a handmade sketch, a small scribble of such a part. And this is your exercise. And some more explanation. This is our grinding nozzle. So it is a part we use in our machine tools for grinding operations. And you can see here the grinding disc in blue, this one. And for this process, we need a grinding fluid. You can see it here. And this is the part. This is here the holder for our nozzle. And this here is our nozzle. So it's a milled part with integrated small pipes. And this is a former version. So at the moment, it looks like this. And we use this part to bring a fluid spray on this grinding disc. And this design is for milling and turning. So it's not for additive at the moment. And what is the task? So create a sketch of a component designed for additive manufacturing. for this part here. And please, think about how to separate the component from the printing plate later on. And perhaps you have some ideas for the production strategy. So how to do the final machining. This one here is optional. So what do I want you to do? So please do not use CAD systems for this. Please use a piece of paper and a ball pen or two ball pens with different colors. So create a sketch and please use black, for example, blacks for the part itself and another color for supports. So often we use red for supports. It could be also blue and green or whatever you want. Use a piece of paper, make a sketch, or you use a digital piece of paper. If you have a tablet, it's also possible. And some more explanation to our part. We have here a cutout of this part. So this grinding nozzle actually consists of a main part, this one. It's produced with a turning machine. And there are small pipes in stainless steel, and they are glued into these holes. And we have some functional surfaces, so they are important. Let's start here on the right side. We have a thread. We need it to connect our nozzle with the main pipe, with our holder. And we have here, this red one is a sealing surface. So we use a hydraulic fitting and screw it here into our thread. And at the hydraulic fitting is a seal, and we need here a flat sealing surface with a good surface quality. And then we need here our nozzles, our nozzle geometry. Important is that we transport or that we bring the fluid on the whole disc. So we need here a length of 40 millimeters. And the orientation on the grinding tool is important, but, and this is important for your sketch, the nozzle geometry is freely selectable. So be creative about a possible nozzle geometry. And even liquid output is necessary. So we have here on the last slide, we have here the dimension of the part. So we have a diameter normally of 22 millimeters, we have a height of 62 millimeters. And in this direction, it's 56 millimeters. But the dimensions may vary. So, and honestly spoken, if you make a sketch, it's not necessary to use millimeter papers and so on. So a rough sketch is enough. Please send your sketch as a photo, or if it's possible as a scan via email directly to me. And
excuse me, shall we scan on the paper or we draw it with something?
Sorry, it's difficult. The audio quality is not so good. I want to have a paper-based sketch. If you want to use a CAD system, you can do it also. But then please send a screenshot.
Yeah, thank you.
You're welcome. And I think to send it to me 26 May, I hope it's enough time. The reason why I choose May 26 is my last session with you is session 13. And I want to give you a short overview about our solution so that I can explain how we solved this problem. And this is May 27. So here in session number 13, I will show you in a short X-course our solution for this grinding nozzle so that you can see a really printed result. And therefore it's necessary, or I hope you can realize it, to send me your sketches until May 26. And this is relevant for the final grade in additive manufacturing here. So these slides are also uploaded to our session folder. So back to our main presentation. So this is very good, our timeline today. So we have 20 minutes left. I think this is enough to show you our robot head. So, and to give you an overview about the main application, we have the so-called robot2go. And here on the left side on this picture, you can see a turning machine. So this is here a machine tool for turning. And we developed a 6-axis robot to equip such a machine tool with raw materials and to bring the finished parts out of the machine. So the goal is to use such a machine tool without, let's say, human capacity. So it's enough to program such a machine, and then the robot will pick raw material from such a pallet and bring the raw material inside the machine. And then the machine will do the turning process, and then the robot will grip inside, take with the one hand the finished part, and in the second hand is already raw material, and then you will grip the finished part, change here the robot head, rotate it, and bring the raw material into the spindle to go on with the machining process. And at the moment, we have an increase of automation solutions like this. So, and we developed a new robot head. This is this triangle part here. And this is the standard design. So you have here the, let's say, pipe for all the channels and pipes for pressed air. Here is the surface for gripper number A. Here is the surface for gripper number B. And at the back side is the area where we connect to the robot head or to the robot itself. And we call it AM quick check. The potential of such a part is to reduce the weight, to integrate more functions. Very important to minimize the number of parts by using an integrated design. Our goal was to increase the accuracy of this head, and this is also important, we need an economical manufacturing process. So, and the goals of the redesign, so as a result, is to maximize the stiffness of our part and to minimize the weight. And the process in this project was, we started with a redesign. Here, this one. Then we print. This is a first prototype. We do the machining on a machine tool, on a milling machine in this case. We did an assembly test, and then finally a load test to do a quality check. And I will give you now an overview about several steps. So first of all, we won't start with the head itself. We will start with our cable screw because it's also printed. Some slides back, we have here this cable to transport all pipes and cables to the head. And here's a part to fix this cable. And we changed the design, so we printed this in 2 parts to reduce the used parts and especially to reduce the weight. This part is printed in stainless steel. And you can see here with the part number 1 at the bottom, and this is part number 2. And this part number 2 is printed with a printed hinge here. So it consists of 2 parts. They are printed together. So you're not able to disassemble them, to disassemble them. And the inner geometry is like the geometry of this cable. So we use these tools here to fix our cable directly with the right geometry because it's printable very easy. And then in the assembled state, you can see it on the right picture. We close this hinge and then we have here 1 screw to fix it. And with this screw, we have enough pressure in this geometry to clamp our cable. And the outside geometry is so designed that we need here this spring again to avoid a crash in this cable. And you can, let's say, we screw on this spring on our outer geometry. And at the end, if you compare it with the traditional design, this is not half a kilo, but more, let's say more or less half a kilo. And we realized here a part with less than 200 grams. So in this case, with additive manufacturing, we reduced the weight around about 60%. And this is especially for automation solutions like robot heads. This is very important. Back to our robot head itself. You can see here on the left side, this is an intermediate step of our design. And it's already printed, but it's not so optimized. So in this case, we have different gripper variations here. So it's possible to add a 2-finger gripper or a 3-finger gripper or a 4-finger gripper. And depending on the type of gripper we have to use. In some cases, in this case for the 2-finger gripper, it's necessary to add here an intermediate plate. And in our former design, it was necessary to integrate here a milled background plate to fix this background plate to the robot and then to assemble our robot head directly to this background plate. And in our second design stage, the goal was to develop an integration of all components. And therefore, we used a simulation-driven design approach with a numerical stress analysis. So you can see here the result. This is only 1 part, and we integrated the whole geometry of these intermediate plates. And we also integrated the background plate in this case. And what is a simulation-driven design approach? So we started to analyze all stresses for this part and all workload. And we used this for a topological optimization. You can see it here on the left side. So we used such an optimization to simulate the stress in the part. And a topology optimization is used to create a geometry optimized for the stress level. So, and this looks a little bit like the inner structure of bones, for example. So this part or this sketch here on the left side looks very organic. And this is because the nature, it's the same approach to optimize geometry to the workload. So this is the optimized geometry. And we're even able to print such a geometry. There will be a lot of support inside, but it's printable. But we got the requirement of our customer to close the outer surface. So we need a closed design to avoid that chips in the milling process will come inside our robot head. And then we developed this shell design on the basis of this result of the optimization. So in this shell design, there is a variation of the wall thickness. So in areas with high stress, like here, the wall thickness is higher than in areas with low stress. And at the end, we use numerical stress analysis to prove our concept. And so you can see here the results. So it's a numerical stress analysis with emergency operations. So with a hard stop of our robot with a part in the gripper from movement, so emergency stop. And even in this case, the stress is the highest point is here around this area, but it's low enough for the whole life cycle of such a product. So we optimized you can see it here, we filled up the inner structure with lattice structure, and we optimized the wall or the stick thickness of this lattice structure regarding to the stress. So in areas with a high stress, we increased the diameter of all these elements, and in areas with less stress, we decreased the diameter. So at the end, if you compared traditional design on the left side and additive design on the right side for the version of a two-finger gripper, so this is here such a two-finger gripper, by using this integrated design, we reduced the number of parts by 60%. So in the standard design, we have 135 parts, and now we have only 56 parts. And we also integrate the function of these intermediate plates. So the intermediate plates are used to guide the pressed air to the right outputs. So you can see here in this transparent view the inner pipes. And if you want to drill pipes in such a part, you have to close a lot of openings here, like marked in red. And we integrate this channel structure directly in our part. So we have here two inputs for pressed air, and we have different outputs. Version A for the three-finger gripper is here, and version B for the two-finger gripper is here. So it's only necessary to close the other version. So if you want to use a two-finger gripper with output version B, you have to close output A, and that's it. It's not necessary to use such an intermediate plate. And by integrating these pipes, we are able to reduce the number of sealing points by 45 degrees, and again 66% fewer parts. So, and we have here a total summary of our robot head. So on the left side, the standard traditional design. So it consists of milled aluminum plates, and in the case of the two-finger gripper, you need these intermediate plates. You can see it here to guide the pressed air to the right position. And if you want to combine them, there are sealing points between all parts. And we have here some key facts. So we have here the weight. So the weight of this assembly group is around about 2 kilograms. We have in red the number of sealing points. So normally 36. And you already saw 2 slides ago, we have in total in this assembly group, we have 135 parts in this group. And to combine it easy, we scaled here all bars to 100%. So our traditional design is scaled to 100%. And our first design stage, so we have here still the intermediate plates and the back plate to connect it to the robot. Even with this design, we increased the weight to 1.2 kilogram. So reduced the weight by 37%. And we also reduced the number of sealing points because they are still the intermediate plates. It's not so much, so it's only 12%. So in this version, even if we use additive for the core part, we have still 32 sealing points because we still have to use this intermediate plate for the two-finger gripper. But even in this case, we reduced here the number of parts from 135 to 82, so by 40%. And then the second design stage, this is our final design, and we start actually the series production of this version. We're here because we integrated here the intermediate plates. We reduced the total weight of this assembly group to 751 grams, and so it's a reduction by 62% in weight. And as I said, for automation solutions, this is very important. And we reduced the number of sealing points, so to the half, let's say, and the number of parts to 56. So at the end, there are still 56 parts in this assembly group. So, and we count all screws and sealings and so on. So this is really a total overall number of parts in this case. And from my point of view, this is a really smart application for additive manufacturing because we used all of the benefits here. And one additional benefit of additive here in this case is the accuracy. So short explanation to this. In this case, we have here one plate here, one plate there, and one plate at the back. So we have 3 milled plates and they are assembled together. And this is very difficult to get a high accuracy of the 2 gripper. So if you want to pick a part with gripper A and then you rotate your robot head to gripper B in this position, there's a lag between position A and B. And because in this case, we have here one part and we milled all 3 main surfaces, the 2 for the gripper and the 1 for the connection to the robot, in one clamping situation, we were able to increase the accuracy of this part by the factor of 16. So we are 16 times more accuracy than in the traditional design. And because of this, we reduced the whole assembly time very massive, because normally there is a lot of work to adapt your part to get the right accuracy. So yeah, in summary, this is one more application for additive and for automation solutions. The lightweight design is very interesting. So with you here on the time, we have 4 minutes left. So this is the content for our second session, the second session for additive manufacturing, the session number 10, one more step ahead. So I hope you got a good impression of the possibilities of additive manufacturing, and that you learned enough about the very basic principles to create a first design sketch of such a grinding nozzle. So I will upload this presentation later on to our session folder, but the design guideline and the slides of the exercise are still there. So if you have any questions in the next days regarding here our exercise or other topics in this session, please feel free to post it in the chat of this session here, or in the overall chat of the Teams channel. Because here I checked in parallel the chat of the session today. There are no questions in the in the chat we have to answer now. So at the end, I thank you for your time, that you listened here to session number 10, and I hope that you got a, let's say, a good impression of additive manufacturing and the possibilities of this cool technology. So thank you very much, and enjoy your evening and stay healthy in this time.
Yeah, thank you, watchers.
Bye bye.
Yeah, bye bye.
Thank you. Thank you. Thank you. Thank you.